The first thing we want to understand is what is a mechanical wave. And a mechanical wave it occurs when a disturbance in a medium uh, carries energy through that medium. So in this picture here, if we drop a pebble in water, the the wave travels through the water, and you'll see this wave traveling along the water. And the water is the medium. For sound, when we talk with each other, sound waves travel through air, and that air is the medium. That's a mechanical wave also. This water wave is a mechanical wave. If you have a wave traveling through the earth, that's a mechanical wave. So whenever you have a wave that travels through a medium, that is a mechanical wave. And then there's some kind of source that causes the wave to occur. And in the case when we're talking, our larynx is the source, or the pebble dropping in the water is the source. There's some source for this wave to occur. Uh, Here we have a wave, a mechanical wave that's going to um, cause these beads to vibrate up and down. We have this source here, this piston moving up and down. And this is a mechanical wave because there's a medium that the wave is traveling through. An electromagnetic wave occurs when you take a charged particle, electron or a proton, and you move it up and down, you vibrate up and down. An electromagnetic wave travels off of that charged particle. Now, an electromagnetic wave does not need a medium to travel through, and examples of electromagnetic waves would be light, X-rays, um, gamma rays. Also, anything on the electromagnetic spectrum, infrared, ultraviolet, all of these electromagnetic waves, radio waves, TV waves, all of these are electromagnetic waves, and they're due to charged particles vibrating up and down. Here's a situation where we can have an electromagnetic wave. We have this transmitter, this radio station can move the charged particles on their antenna, and it would send out an electromagnetic wave. And you see, if you watch the electron on the receiver where the house is, where they have the antenna, that electron will start moving up and down at the same frequency. And you see this wave traveling along. It's propagating through the air. But what I can do is have it actually oscillate here. And we can see this charged particle moving up and down, sending a wave. And the electrons in the antenna would also move up and down at the exact same frequency. So these are electromagnetic waves, radio waves going through the air. We're not going to talk about matter waves too much in this class. This is just maybe from chemistry. You were talked about how an electron is a particle, but it can also act like a wave, especially when it goes around the nucleus. If you have the nucleus here and the electrons go around the nucleus in a wave-like fashion, that's called a matter wave, whenever particles travel in a wave-like fashion. So one of the more important things you have to know is what is a transverse wave. And a transverse wave is a wave that is S-shaped. It's sinusoidal, moving up and down. And a good example of a sine wave is taking a rope or a piece of string and moving your hand up and down and sending a pulse down the wave. That is a transverse wave. A longitudinal wave is this one, where this is like a sound wave, where before the transverse wave, um, electromagnetic waves or light waves are really good examples of transverse waves, where longitudinal waves, these are sound waves. And so if you take a slinky or something and you push and pull on it, you're making the waves travel, you're making the wave travel down the line, and the objects in that wave are vibrating back and forth. So that is a longitudinal wave, where you don't have the S shape, you just have the straight line, but the molecules in the slinky are just vibrating back and forth. So we're talking about how to solve for the speed of a wave on a string. And in order to do that, there's an equation that the speed on the string is equal to the square root of the force of tension all over the mass per unit length of that string. So that mass per unit length is also called the linear density. It's the instead of regular density where it's mass over volume, this is linear density where it's mass over length. And so they use a mu symbol for that in the textbook, mass over length. And so in the textbook you see this equation here, square root all over the force of tension all over mu. Now this simulation here will let us look and see what the tension does for the speed of the wave. If I send a pulse down, um, if I send a pulse down, you see this wave travel downward and it comes back and goes back again. And the tension is very high. Now I'm going to decrease the tension here. We'll pause this, and I'll decrease the tension. I'll lower it down, and let's see what happens to the speed here. We'll send a pulse. Let's restart it. And we send a pulse. And you see it's much slower. I've decreased the tension on this string, and so it's a much slower velocity. So the equation follows this motion. Um, so you can see according to this equation here that the force of tension, if you increase the force of tension, you increase the velocity of that wave. That's really one of the important ideas here. It's a square root relationship, but increasing the force of tension increases velocity. Now, if you increase the linear density, then you're going to decrease the volume, the velocity of that wave. So we could do some problems that deal with this idea. So here we're going to look at the speed of a wave in a gas, and a sound wave is the best one to look at here. So the speed of sound in air is 331 meters per second at 0 degrees Celsius, and it's 343 meters per second at 20 degrees Celsius. The change in temperature changes the molecules in the air, allowing the sound to travel faster through the air at that higher temperature. So what we're going to do is a nice simple equation here. In the textbook, they have a more complicated equation that we're not going to use. But we can always solve for the speed of sound in air as being 331 meters per second plus 0.6 times the temperature in degrees Celsius. We're going to look at what's the general formula for finding the speed of a wave. Well, we know that to find the speed of anything, the average speed of anything is distance over time. And if we're looking at waves, and we look at a wave traveling, the distance we can look at is actually a wavelength. And so from the starting position to when it starts to repeat it, that 2 pi, that's called one wavelength. And a wavelength has this strange symbol of an upside down y called lambda. So that's 1 lambda. And so our velocity equals lambda. 1 wavelength is our distance, and our time is going to be the period, capital T, because that's the time for one oscillation. And so that's one equation we can use, but more commonly you'll see us use frequency equals 1 over the period, and then plugging, or the period equals 1 over the frequency. And if you plug that in, you get this other equation, velocity equals frequency times wavelength, which you'll see quite often when solving for the speed of any wave in a material. So here what we're going to do is we're going to look at a wave traveling down a string, just like what we saw earlier. So I'm going to send a pulse down here, down this wave. We're going to make it a higher tension. And so we're going to restart this. And here we're sending a pulse down. I'm going to pause it. So as you saw, that pulse was traveling from left to right. Well, we're going to look at the same thing in this section, where here we have this pulse traveling from left to right. So it's traveling along, and what we're specifically going to look at is what's going on with this point here. So this point's right here, and this wave travels and what a wave is just really a transfer of energy. A wave is just allowing energy to transfer from one point to another. It doesn't transfer the material, it transfers the energy. So if you look at our previous example and we restart it, we send a pulse, these beads, this particular bead doesn't travel left to right. It actually travels up and down, and it travels in simple harmonic motion. So this bead moves up and then down, traveling in simple harmonic motion. And if you go step by step, you can see that bead now is down here, that same bead. And you go step by step, that same bead, so it went vibrated up and down. So that one bead doesn't go from left to right, it moves up and down. And if you take a look at another bead, and we do this from left to right, you can see that that bead just moved straight down. So these beads move up and down in simple harmonic motion. And so when we look at this this picture here, we're just seeing this one bead here move up to here, and then back down, and then back down again. So we're just watching it move up and down. And then this history graph just shows that, just shows that that point, that position change.